So we've just come off several lessons in which we've talked about acid-base titrations. And no acid-base titration would be complete without a discussion of indicators. In this lesson, we're going to define what an indicator is, and we're going to describe how one works, and select an appropriate indicator for a titration if you're given Ka values. An indicator is simply a substance which changes colors with pH. They are usually weak organic acids. They have an H. They're usually written with something and then the COOH. What that represents is a C with a double bond O and the OH group attached. So many of the organic, not all, but many of the organic acids have different colors depending on whether they're ionized or unionized. So if they have the H attached, they would have one color, and once the H has been dissociated or it has been donated, it will have a different color. So HIN I'm going to use to represent my indicator. The H at the front is showing that it is an acid. And as an indicator, if it's placed in an aqueous solution, it will be undergoing this equilibria. And this equilibria is such that, well, this acid is such that it has got a certain color, and I'll call it color A for the acid form and color B for the ionized form. This indicator will undergo changes in its equilibrium according to Le Chatelier's principle. Okay, so I want to guide you through this concept of understanding how it changes color with several questions. So you'll be asked to answer several of these as we go through this process. Okay, so the first one is, which way is this equilibrium going to shift if you add an acid? Now, Le Chatelier's principle is in play here, so if you're adding an acid, you're increasing the concentration of that substance. So determine which way it will shift. Well, if you said to the left, then you're correct. Anytime you add a substance, it will shift away from that substance in order to reestablish this equilibrium. So if it's shifting to the left, when you add an acid, what color are you going to see? If you said color A, then you are correct. Okay, let's keep working through this. If you add a base, now if you add a base, you'd look at that reaction and say, well, there's no OH minus listed in there, but we remember from our acid-base chapter that when the H3O plus goes up, the OH minus goes down, and vice versa. Okay, so if you're adding a base, you are adding OH minus. So the H3O plus has got to decrease. So now, if you add a base, which way will this equilibrium shift? Well, if you said to the right, then you are correct. Now, if it shifts to the right, what color are you going to see? If you said color B, then you are correct. So this is the process of how an indicator works. It is added to this acid-base titration. And you've got within your flask maybe an acid, and you're slowly adding a base. And as that amount of acid and that amount of base is changing within the course of that, it is affecting the quantity of the H3O plus in that solution. And as you're affecting the quantity of the H3O plus in that solution, you are affecting where this equilibrium lies and how much A there is or how much color B there is. And as you get more and more color A, or this HIN in the solution, the color A will become prominent. If you get much more of the ionized form in there, then the color B would become prominent. So you need to find an indicator that changes colors near the pH of the equivalence point. Anywhere near that upward slope, now we know that each one of these had this steep climb, so anywhere in that upward slope, if it would change colors anywhere in a pH there, then it would be a good indicator. Now, how do you find one that changes colors in that range? Well, first of all, let me define endpoint. Endpoint is the point where the indicator changes color, and so that is its switchover. There is some point where there's equal amount of HIN and IN minus. At that point, you'd probably see a color somewhere in between those two. So we've got purple and red, and it's going to be a purplish red. You're not going to see a distinct color change until IN minus is predominant. But where that color change occurs is called the endpoint. Our goal is to make the endpoint match the equivalence point as close as possible. So here's the upward slope of this one, and if you followed this beginning point and this ending point down to the graph, you'd probably just have a tiny range. Just a few drops would switch through that range. So if you could get an indicator changing color in this range, the way you find it is you do the pKa of that indicator, and this will tell you where the color change would be. Now let's think about why the pKa would do that. If you've got the reaction of the indicator, and I'll write it down here, in which you have got a significant amount of both the HIN over here and the IN minus, well, you've got a weak acid and its conjugate base, and you have a buffer. So the Henderson-Hasselbalch equation would apply. And if the Henderson-Hasselbalch equation applies, and we'll write it, pH equals pKa plus the log of the base, which is IN minus, over the acid, which is HIN. When there's equal amounts of HIN and IN, this term is 0. So pH equals pKa. So if you know the pKa of the indicator, you're going to know the point at which you have equal amounts of both of these, and that's the switchover point for the color.
In this demonstration, we're going to be looking at indicators. And indicators are used to help us know when the equivalence point is reached in a titration. We call it the endpoint, the color change. The indicator I've put in this flask is Bromothymol Blue. And Bromothymol Blue doesn't look blue. It's yellow right now because it's yellow when it's acidic. And I have placed some hydrochloric acid in here, and I would be titrating it with some sodium hydroxide. Now this video is not about proper titration techniques and all of the work that goes into doing a good titration, but I do want to show you that change of color. So I will be adding the sodium hydroxide, and it's going to take a little over 10 milliliters because I had 10 milliliters of the HCl in there. And as it starts getting close, I can see a little bit of blue starting to form, and then I can swirl it away. Eventually, one drop will turn it from the yellow, and then we'll see the blue. There it is. So there's the blue color. So in a good technique of titration, you'd slow down that process. But this lets us know that we've switched our pH, and you choose an indicator that changes colors at around the pH of the equivalence point. We are doing the same titration but with a different indicator. This is phenolphthalein, and phenolphthalein will change from colorless to pink as it reaches its endpoint. As we put a little bit of the base in, we'll see a pool of pink forming that as I swirl goes away. This is sort of like adding hot water to a cold bathtub. It's hot in that one spot but then dissipates throughout. The base is dissipating and reacting with the acid. But if I hit it just right, I will go from one drop where it swirls and goes colorless to the next drop, it'll be pink. I'm getting close. It takes a little longer for the pink to go away. And there we have the endpoint.
Now this is just giving a whole array of various indicators and how they change color. And you see it's kind of a gradual thing. Maybe this is the acid form of this one and it's yellow. And this is the HI or the IN, the ionized form, and it's blue. There's going to be a significant range in here in the middle where it's green because you've got a little bit of both present. This indicator would not be a good indicator for a titration between a weak acid and a strong base because those are above 7. So it would be a terrible one for that. So you have to choose an indicator that changes color in that upward slope. So this is the end of learning objective number 8. We now know what an indicator is, we know how they work, why they change colors, and how to select an indicator for the pH range that you're looking for in your acid-base titration.